I will use another method for measuring the susceptibility of diamatic or paramatic material. So, in this method we have to use a solid sample, just unlike this Quine's method. In Quine's method we use the solution liquid sample, whereas in Gauss method we use the solid sample. Okay. So, experimental are quite similar, only this force measurement are different. So, measurement of magnetic susceptibility of diamagnetic or paramagnetic materials by Gauss method. Okay. So, Gauss method is similar to Quine's method, as already I have demonstrated this Quine's method in laboratory. So, this we have measured, we have prepared the solution of manganese sulphate, and using the solution how that experiment is done, there basically height change of the liquid was the measurement parameter as a function of magnetic field. So, in this case, in Gauss method the substance is taken in a powder form or solid form. Okay. It can be powder form or this it can be solid rod also. Okay. Whereas, in Quine's method the substance is taken in liquid or solution form. So, this is the basic difference, but their working formula this theory is basically same for same starting theory, but final form is slightly different. So, there because in Quine's method we are measuring the height change of the liquid, and in this method basically we will measure the weight change of the sample. We will measure the weight change of the sample, apparent weight change of the sample, okay, using the balance. So, the working formula is F, here I have written small f, earlier in that case capital F I wrote. So, small f I have written. So, that is half mu 0 chi dH2 by dx. So, this is basically energy density I told, but this also one can tell force over unit length, okay, force over unit length of column. What is column? Column is either it's a sample in rod shape or powder sample put in a tube. So, it will form a column. Okay. So, why we need column form or tube kind of things? Because this condition is we have to use the inhomogeneous magnetic field. So, some part of the sample has to be outside of the field, okay, magnetic field. Then only we can use this. We can think of this the variation of the magnetic field. Okay. So, now if we tell this force over per unit length of the column. So, now if you have this column, the sample having the length say L, length L, and this area, cross section area is A. So, now the force we can tell F per unit length. Now, that dx, for dx length, what is the force? That will be the force. Now, with that if I multiply this with A, then it will be basically volume. A into dx, it will be volume basically. So, if you if you integrate over this length where the magnetic field variation is there, so you will get this part, okay. You will get this part. So, field from varying from the 0 H0 to H over the length, some say 0 to L length of the sample. So, you will get this F equal to this. So, this one can tell this as if this is the total force acting on the acting over the volume of the sample, okay. So now this force, because of this force, the sample weight, so force, this weight of the sample, how it comes? Because of the gravitational force, weight we get of the sample, the gravitational mg. So g, so that force is basically downward. So weight and this force is equivalent. So now if some force is acting on this, so it will feel that its weight will be is lighter. It will feel lighter. Okay. So that's what it will happen if it is paramagnetic material. So force, say, it will be upwards. In diamagnetic material, this force will be downwards. Okay. So what will happen? So this apparent weight of the sample will change due to the force, this force, magnetic force. So this magnetic force, so I can measure this magnetic force using the balance. So initially whatever the weight, now this weight will change due to this force. Now to get back this original position, okay, what is the weight I have to put in the balance? So that from there basically so that extra weight I am putting to get the initial position of the balance before applying magnetic field. So how much mass I have to put? So that is, if it is that del m, so del mg, so that will be the weight change of this sample, okay. And this del m basically, as I told, this A into L, so that will be the volume of the sample, okay, and into rho, density of the sample. So that is basically delta m. So balance with change of weight, so that is del mg, so change of the mass, okay, and corresponding the change of the mass. So that mass, that change of the mass of what? Change of the mass of the what? Apparent change of the mass of that sample due to that force, okay. So that we have to take from this our sample in terms of our sample dimension, and this is density, okay. So here basically chi you are getting, chi equal to so this will be balanced by this will be balanced by this, okay. So from that chi equal to, you will get 2g del m by mu 0 AL A square, okay. So this part you can see, these are all constant, the dimension of the sample, okay. So if I can measure the change of the mass, apparent change of the mass of the sample as a function of magnetic field, so we will plot del m versus square of the magnetic field. Then from the slope of that curve, we will get, this will be the slope, this will be slope. So this will be equal to from the slope of the curve basically we will get chi into mu 0 A L by 2 G. So, this is a constant. So, chi by this constant will be the slope. That slope we will get from the del m versus square of the magnetic field graph. So, that from there you can find out this chi, this susceptibility of the material. So, this Guy's method and Queen's method, in both method we are measuring the susceptibility of the diamagnetic or paramagnetic material. So, this in sample form is different. So, in Queen's method it is a liquid form of the sample, and in Guy's method it has to be solid form and columnar form, okay, either rod form or the powder in a tube, because the sample in both techniques. So, it has to be in lengthwise, the sample should have the length either in liquid column or the solid column. The reason is that there should be variation of the magnetic field over the space. So, that means the inhomogeneous magnetic field sample has to be in inhomogeneous magnetic field. So, that is the reason that the sample shape either liquid or solid, it has to be in column form or tube form. Okay. And then in one method we are measuring the height change of the liquid, and another method we will measure the mass change, apparent weight change of the sample over the magnetic field, and plotting the graph with height or change of mass versus the square of the magnetic field, and from slope one can find out the susceptibility. So, this for Guy's method. So, in Guy's method, as I describe this working formula, so we will take then we have to take the experimental data. So, in this experiment we need again magnetic field. So, we will use electromagnet. Whenever we will use electromagnet, we have to calibrate the magnet, this magnetic field versus coil current. So, first one has to do calibration of the electromagnet. Okay. Then second, we have seen that we need the AL, means area and the length of the sample. So, volume of the sample and mass of the sample that you have to measure, or it has to be supplied by the it has to be supplied by the lab. So, volume and mass of the sample that we need, and then next this main part of this experiment, measure weight or mass difference between initial weight for H equal to 0, okay, when there is no magnetic field, what is the weight, and then final weight in presence of magnetic field, that is basically, that will be basically del m. Okay. So, del m for different magnetic field. So, we will measure del m for change of mass, change of apparent mass basically. This is not a real change, because this change looks because of the force coming from the magnetic sample in presence of inhomogeneous magnetic field. So, we have to take data just changing the magnetic field and measuring the del m. So, then we will plot del m versus A square, magnetic field square, and from the slope we will find out chi. Now, here in our laboratory we will use basically aluminum rod for this experiment, that is paramagnetic material. So, from the after measuring this chi experimentally, then we can use this formula. This is a very well known formula. This chi, that is basically m by h, that is equal to n mu 0 p mu b whole square divided by 3 k t. Okay. So, k of course Boltzmann constant, that is known. Mu 0 is basically this permeability of in vacuum. So, that is also known, and n, this n is what is this n? N is Avogadro number, this n is Avogadro number, that is also known. N is Avogadro number, that is also known. Now, here actually this is mu square, magnetic moment square, mu square. So, that we have written P mu b square. Mu b is the Bohr magneton, and P is called the magneton number, and P mu b is called the effective Bohr magneton. Okay. So, if I know this chi and this other Avogadro number mu 0, other things is known, mu b also known, Bohr magneton. So, then we can find out this P for this material, P, that is the Bohr, that is the magnetron number. Okay. So, and one can compare with the theoretical value of P. So, theoretical value of P one can find out. So, using the basically this for aluminum, what is the what will be the magnetic moment? What will be the magnetic moment theoretically? So, so that one can find out. So, this P is theoretically P is equal to G square root of j plus 1. Okay. And G is Lagrange factor 1 plus j plus 1 plus s plus 1 minus l plus 1 divided by 2 j plus 1. So, for aluminum atom, what is the L value, total L, what is the S value, okay, and what is the J value. So, if you know, then you can calculate G. Now, from this using this one, G into this j plus 1 square root of j plus 1. So, this theoretically you can tell what should be the P. So, now this P you can compare with your experimental value getting from the measurement of this chi. So, you can compare this experimental value with the theory value. If any discrepancy is there, so why this discrepancy is coming, one can explain, or if it is matching well with this theoretical value, then it's fine. Okay. So, so this experiment we will demonstrate in our laboratory. After this discussion, now I think in next we are going to demonstrate this experiment in our laboratory. So, I will demonstrate this Gauss method for measuring the susceptibility of solid paramagnetic materials. In our laboratory, we will take the aluminum. So, this is the aluminum bar kind of things. Okay. So, this is our sample. Aluminum is made of aluminum. It shows the paramagnetic property. So, this sample now in Gauss method, so we will put this end at the center of the pole pieces of electromagnet. So, this end will have the maximum magnetic field, and this other end, other side, it is outside of the magnetic field. So, this rod, aluminum rod or bar, it will see the variation of the magnetic field along the length. So, basically that is the condition inhomogeneous field, condition of inhomogeneous field, okay, for this experiment, and because of that it will feel force either downwards or upwards. Thus, the weight, apparent weight or mass of this sample will decrease or increase due to the force, okay, and that force because of inhomogeneous magnetic field. So, what I need to apply the magnetic field, and then for that magnetic field there will be force acting on this sample. Now, how much equivalent mass changes, how much equivalent mass of that force changes for this rod, that we have to measure. So, in this method balance is used, very sensitive balance, it is in milligram sensitivity balance we need for this experiment. And if this setup is in a closure, so that no air should pass through it, then it is better. So, here this is the experimental setup for Gauss method. Okay. As I told, we need electromagnet. So, here you see this electromagnet, and this rod is hanged from this balance. This is the digital balance. So, from the bottom of this balance, okay. So, this aluminum bar is hanged between the, you see this, between the pole pieces. This here we have used tapered pole, okay. So that field will be maximum at the center, and then there will be larger variation of the field along the length of this rod. So, this end is between the pole pieces, you can see there between the pole pieces of the electromagnet, and other end is attached with the balance. Okay. So, this setup is very compact system, ready-made system. Okay. So, what we have to do, we have to, as I have shown you the formula chi equal to some constant parameter, where this dimension of the rod, this width, thickness and the length of the rod should be known, and density of this aluminum material should be known, G value is known to us. Okay. So, one has to measure this. So, here this is the 10 millimeter, this width is 10 millimeter, thickness is around 2 millimeter, okay, and length is 20 millimeter, 20 centimeter, okay, and it is a density of this aluminum. So, from one can get from this from the literature. Okay. So, this parameters for this sample is known to us, or we can measure and note down. Now, we have to hang from this balance. So, this is already there, because I cannot disturb that one. If you disturb, then to make it to be stable, it takes time. Okay. So, this is the same sample we have put there. So, now what we have to do? We have to initially we have to take the reading of this rod. Okay. So, we have to note down that the initial reading, and then that initial reading in mass. Now, I will apply magnetic field, I will apply different magnetic field, and each magnetic field, what is the reading of the balance. Okay. So, difference of these two reading will give me the del m whatever we have seen in formula. So, your magnetic field versus del m or del m versus magnetic field, that data I will get. So, in this balance here, this facility is there. So, I can initialize the initial mass as a 0. Okay. So, then what will happen? I need basically del m, so change of the mass. Okay. So, now I will apply magnetic fields and whatever the reading. So, that is the directly I will get change of the mass del m. So, I will note down the as a del m, this whatever the reading I will see in this balance. Okay. So, now you see this this reading is here you can see this reading balance, it is initialized, this you can see this balance, it is 0 reading 0.0000 gram. So, what does it mean? It means that this I will get reading up to 4th digit. After decimal up to 4th digit means it is a 0.1 milligram. 0.1 milligram is the least count of this balance. Okay. So, now field is here, you can see this electromagnet. So, I have Gauss meter also there, Hall probe and Gauss meter here I have. Okay. So, before starting experiment, one should calibrate this electromagnet, okay, this current versus the magnetic field from this Gauss meter. Okay. That calibration will be used for knowing the magnetic field for corresponding this coil current of electromagnet. So, now you can see this reading, now it is 0. Now, I will apply magnetic field, say I am applying magnetic field, some field I am applying is changing, okay, so 0.55. Okay. So, this coil current is 0.55. Okay. Now, here, so we have to give some time to stabilize it with very sensitive this balance. Okay. So, here you see it has come this 0.0011 gram, that means 1.1 milligram. So, this is del m, as I told this initially. So, we have option here to this initial weight mass of this rod, weight of this rod to make it 0. So, I have made it 0. So, now from that 0 whatever the change, that is basically delta m. So, here it is so it is 1.1, now it is showing 1.2. So, that is the for this field or this for coil current corresponding field you will get from the calibration. So, you note down. So, this coil current 0.5 I think 5 ampere, then you should keep one column H, corresponding H from the calibration curve one has to take, from the calibration curve one has to take. Okay. So, now I will write del m. Okay. Del m is here, it is a It is the 1.1 to 1.3, this some variation is there. So, one can take average 1.2 milligram. Okay. So, now I will change to next value, say next value I will take 1, okay, it is the 1 ampere. Okay. So, for 1 ampere coil current, what is the magnetic field that I have to take from the calibration? Then here you have to wait. Here it is showing this 3.4 gram, it is showing 3.4 milligram, not gram. So, we are noting down this change of the mass del m. Okay. So, this way for different field, I will go maximum field. Here we can go up to 3 or 4 ampere current. Okay. So, up to that 3 or 4 ampere current I will go, and then I will decrease again in step 0.5 step approximately, and I will note down the reading. So, during increasing the magnetic field, during decrease the magnetic field, we can take data and take average. For same field, we can take average of these two data, or we can plot separately this for increasing of the magnetic field and for decreasing of the magnetic field, and then we can actually find out the slope from the plot delta m versus a square, and then we will get from these two slope whatever we will get. So, we can take average of the slope, or we will find out chi from this each slope, and then we can take average of this these two value as a our result. Okay. So, it is a very nice that when I am increasing, let me go to 1.5, then okay, it is a 1.5. Okay. So, 1.5, so now reading is 1.2 milligram, 1.2 milligram. Okay. So, I will go to the next value 2. Okay. So, 2 ampere current, and here his value is 12.5 milligram. Okay. So, this way if, go up to the highest current, and then again come back to the 0 value with step of 0.5 ampere current, and we will get a set of data, important data for this experiment, and plotting the graph from the slope we will find out the chi value. After getting chi value, as I told, you can calculate for aluminum what is the magneton number P, and you calculate from this using the experimental value of chi, using that formula as I showed you, n mu 0 p mu v square whole square divided by 3 kT. Okay. From there we can calculate P if we know the chi value, and we can compare with this. So, this is the experiment, it is called Gauss method, which is used for measuring the susceptibility, magnetic susceptibility of paramagnetic or diamagnetic material in solid form. Okay. In liquid form, we use a Queen's method. This same thing for measuring the susceptibility of a sample in solid form. So, I will stop here. Thank you.